Use a line integral to calculate the total work done by the force vector field moving a particle along the helix from when the value of the parameter is 0 to 3 pi. The formula for the total work done has a very common shorthand, which is F dot dr. But what this shorthand actually means is that we're going to take that force vector field function and dot product it with the derivative of the position vector, and that dot product gives us a scalar function that will then integrate with respect to t. So the first thing that we need to do is to write our force vector field function in terms of t. And we do that by looking at the position vector function to get the parametric equations for x, y, and z. So this is our parametric equation for x, this is our parametric equation for y, and this is our parametric equation for z. And then we plug these parametric equations in for x, y, z in the force field function. There's another shorthand for this process, which is that we basically consider taking the position vector function and plugging it into the force vector function. But what that does is it gives us our force vector function now depending on the parameter, which is what's needed to integrate with respect to t. So let's insert one more step here to say that the original force vector function was x, negative x, y, and z squared. And when we plug those parametric equations in for x, y, and z, this first component is just x. Well, x was cos t, so this becomes cos t here. This second component is negative x, y. Again, x is cos t, y is now sine t, so this becomes negative cos t sine t. The third component is z squared, and the z parametric equation is t, so this third component then becomes t squared. Now let's clean this up and then move to the second step, which is to find the r prime t vector function. Let's recall that the position vector was cos t sine t t, so r prime t is going to be minus sine t, cos t, and 1. Now we're going to take our force vector function that depends on t and dot product that with r prime t vector function, which is going to give us some scalar function that will then integrate. So this dot product is cos t times minus sine t plus minus cos t sine t times cos t. So let's then call that minus cos squared t sine t plus t squared times 1 is just going to be t squared. And now it's time to set up our work integral, where this is our integrand. And the limits of integration, we're going to go from t is equal to 0 to t is equal to 3 pi. So let's split this integral up and handle each of these pieces individually. Here let's let u equal to cos t, so that du is minus sine t dt. So this integral becomes u du, whose antiderivative is u squared over 2. And when we convert back to t, we end up with 1/2 cos squared t. Let's do the same thing with this middle integral. Again, we'll let u equal to cos t, so that du is negative sine t dt. This negative out here becomes part of our du substitution, and we end up with the integral of u squared du, whose antiderivative is 1/3 u cubed. And so when we take that back to t, we'll be adding 1/3 cosine cubed t. And this third integral is going to evaluate to being just t cubed over 3. So we'll add that in down here and then evaluate this entire antiderivative from 0 to 3 pi. So we plug in 3 pi into the antiderivative, and from that we subtract the lower limit plugged in, which is 0, and then simplify to get 9 pi cubed minus 2/3. And this would be measured using some work units.